Again, bursts of electricity will be produced. Each burst can be as powerful as a small lightning bolt. Each fusion power plant design will have a characteristic number of bursts per second. For example, let's imagine a particular design has 1,000 bursts per second. The frequency of AC electricity in the United States is 60 hertz, so that won't work. 1,000 hertz would not be directly compatible with 60 hertz, so something must be done. Something must be done to modify the cycles per second. Each of these powerful bursts of electricity would be way too large to go directly into the electrical grid. So, something must be done. Something must be done to make these lightning bolts of electricity be less dramatic. Think in terms of spikes. In this image, we have huge spikes coming out at 1,000 hertz. This is what we want. Small, smoothed out waves repeating at 60 hertz. We want nice, clean, alternating current electricity. I thought of trying to put both of these graphs in the same graphic. It's simply not reasonable from a visual point of view. The height of the massive spikes overwhelm the height of the alternating current. Comparing 60 hertz to 1,000 hertz is also visually difficult. Also keep in mind, 1,000 hertz is just an example. Only experiments will tell us what the best frequencies will be. Perhaps a 1 meter system will work best at 24,467 hertz or some other value. I don't know. Not yet. To summarize, in step 1, powerful spikes of new electricity are being produced. The spikes are too powerful for the grid and their frequency will be wrong. That leads us to our next step. In step 2, each huge pulse would need to be dampened. In general, this is no mystery. This is not tricky. Every surge protector in your home and office has a circuit designed to do something similar. However, top-notch electrical engineering will be needed for an efficient and robust design. An efficient design is needed so energy will not be wasted. A robust design will be needed so the parts will not vaporize. We don't want to be repairing or replacing the circuit every day. Step 3. After each pulse of electricity is dampened, it will need to be temporarily stored. This electricity is still not suitable for the electric grid. There is still the problem with the mismatched cycles per second. The frequency is still wrong. Plus, you want to temporarily store the energy in order to deliver it to the grid in the way that meets the real-time demand. The solution is to use superconducting energy storage rings. Now, an SES ring has a shape similar to a tokamak. Instead of the current flowing around as a hot plasma in an SES ring, the current flows around inside of a superconductor. In this graphic, imagine the red loop is the superconductor. First, electricity produced from the fusion power plant is injected into the SES rings. Then, electricity stored in the SES rings is injected into the electrical grid. SES rings are systems that can both store electrical energy and cleanly feed that energy into the electric grid. Here, in step 3, we are only considering the energy storage issue. After the pulses are dampened, they are stored in the SES rings. Step 4. Finally, after taking a brief pit stop in the SES ring, the newly generated and accumulated electricity will safely and cleanly be released into the electric grid. Acting together, the special circuit and the SES ring system will convert the difficult pulses of DC current into nice sine wave AC current. The 1,000 hertz pulses will be converted to 60 hertz pulses. Many years ago, I read that SES rings can respond to the electric grid in 1/4 of a cycle. If they have not been improved on since then, that means they can adjust their output to match demand 240 times per second. That's impressive. The classic example is this. Imagine a sawmill in Wisconsin starts up a powerful electric saw for cutting logs into lumber. When this saw is turned on, The saw's sudden high electrical demand could cause a brownout over the entire area's electric grid. It might even trigger a blackout over a larger area. An SCS system can sense this demand almost instantly. It can dump extra electrical energy into the grid so there is no brownout. That is a nice feature. So one role of the SCS ring system is to automatically monitor the grid and feed energy into it as needed. At this point, the electricity has been produced. At this point, it is up to the electrical engineers to worry about the fine details. This will be high quality, 60 Hz alternating current electricity. So, the SCS rings will not be capable of directly handling the powerful spikes of electricity that are being generated at the core. A special circuit between the confinement circuit and the SCS ring will be required in order to dampen these powerful spikes. Then, after the SCS ring system has acted as a buffer between the production of electricity and the consumption of electricity, this nice high-quality electricity will be fed into the grid. Again, SCS rings are nothing new. They are already in use. If these SCS rings cannot be made large enough, then each containment circuit would need multiple SCS rings. These SCS rings are expensive components. I wouldn't be surprised if the SCS ring system end up being 50% of the cost of these fusion power plant designs. To recap, 1. As the fusion fuel is burned in the core, the spherical electromagnetic confinement field converts the powerful pulses of plasma energy into powerful pulses of electricity via the MHD effect. 2. These powerful pulses of electricity will be dampened in a special circuit. 3. Then, this electricity will be fed into an SCS ring and temporarily stored. 4. Then, as needed, the SCS ring system will convert this stored electrical energy and feed it into the grid. Keep in mind, the special dampening circuit will require some significant electrical engineering. However, this engineering is straightforward and does not require theoretical breakthroughs in physics. Also, keep in mind, over the last 50 years of fusion research, just about every other major question with regard to fusion has already been extensively researched and answered. We can thank the fusion researchers that have worked on this for over 50 years at national laboratories and universities for this extensive knowledge. We understand how to make the fusion fuel pellets. We understand how to make fusion energy laser systems. We understand how to implode fusion fuel pellets with lasers. We understand how to shield neutrons. For example, the NIF lasers far exceed what my designs will need. In other words, almost 100% of the research needed to make a commercial fusion power plant has already been completed. After the demo power plants are finished, because the licensed designs would be built elsewhere, the work at my fusion energy lab would settle down. Financially, at this stage, my fusion energy lab would be self-funded. No additional government funding should be needed. The goals of the lab would shift to creating variations of the designs and to optimizing the designs. Tests would be done that would improve output, improve reliability, improve safety, reduce size, reduce downtime, and improve many other aspects. Gradually, over time, the licensed manufacturers would have their own research teams entirely take over this role. Again, my small fusion energy lab would only make examples of how to build these commercial fusion power plants. It would not be my goal to have my lab mass produce them. Yes, my lab will have to prove physics and prove concepts. Yes, my lab will have to perform some experiments and prove the engineering. Yes, my lab will have to prove safety. Yes, in the beginning, the demo power plants will not be fully optimized. After this work is completed, the designs for each class would then be licensed to the energy companies, and then they would manufacture them. They would be responsible for the final designs. Initially, very little new technology will be needed. Keep in mind, there are already companies out there that make almost 100% of everything my power plant designs will need. Only a small number of components will need to be fabricated from scratch. First, I'll need a large number of big, high-quality copper spheres. Initially, they'll be fabricated in-house. I'll need to hire a team of people that will do nothing but manufacture these spheres. Many engineering tests will be done. Many variables will be analyzed. What metals are best? Is carbon black the best filler material? How about a castable ceramic? I don't know. We'll have to test things. How spherical do these spheres need to be? This property is called sphericity. Later, this team will research the superconductivity characteristics of these conducting spheres. Second, I'll need to hire a team that will become the experts on hemispheric coils. I need to teach them the basics and set them loose to build and test. I'll need to hire a physicist that does nothing but study these coils. I'll need experts in high magnetic field research. These people already have experience making powerful coils. I'll need technicians that are good at fabricating with carbon-carbon fiber matrices. I'll need a team that has expertise on high power switching. Initially, my lab will purchase products that are already out there. Later, I hope my team will improve on these products so they are engineered specifically for each power plant design. I would need an expert on electric valves, especially someone that has experience with very high power diodes. Just keep in mind, these fusion power plant designs are relatively simple designs, can be built quickly, and will be relatively inexpensive to build. When I say relatively here, I am comparing to a coal power plant or a nuclear power plant or a hydroelectric dam. They should cost less and produce more. Simple, quick, cheap.